Last up for this worksheet is topic 4, which is the product and quotient rules for other roots. So we've talked about the product and quotient rule for square roots. Now we're going to look at other roots like a cube root, a fourth root, a fifth root, a sixth root, okay? So the definition here is for all real numbers where the indicated roots represent real numbers. That's kind of a mouthful, and I'll explain what that means in a minute. We have that if you have the nth root of A times the nth root of B, that equals the nth root of A times B. Or if we had the nth root of A times B, we could break it down as the nth root of A times the nth root of B. Similarly, if we have the nth root of A divided by the nth root of B, that could be made to one just radical of the quotient, so we could have the nth root of A over B. We just have to make sure B is not 0. And then if we had the nth root of A over B, that could be written as the nth root of A divided by the nth root of B. Again, we have to make sure B is not 0. So what does this mean? Well, we have to kind of go back to the previous worksheet. When we have an index other than 2, so you can have an index that's higher than 2. So 2 is just a square root, and then you could have an index of 3, 4, 5, 6, 7, whatever. If n is even, A and B must be non-negative. So that's what they mean. For all real numbers where the indicated roots represent real numbers, well, when you have an index that's even, you can't have a negative radicand. You just can't. You can't have a negative square root. You just can't. There's no way to have an even number of identical factors that have a negative product, okay? So everything has to be non-negative if n is even, okay? If n is odd, A and B can be any real number. So please keep that in mind. So when the index is even, all the rules for a square root apply. When the index is odd, all real numbers. You can have positives and negatives everywhere, okay? So be very cautious of what your index is. Even, everything has to be non-negative. Odd, any real number. The other thing that you really have to be careful with here is the index must match before merging expressions. Hopefully that kind of goes without saying, but you do want to be cautious. So like right here, when we look at the nth root of A times the nth root of B, before we can merge that under one radical expression, we have to make sure the index is the same. You cannot merge like a third root and a fourth root. It just doesn't work. You have to merge, third roots with third roots, fourth roots with fourth roots. Okay, so you do have to make sure the index matches. Now let's use that idea to simplify here. So we're going to look at the cube root of 54. So this one doesn't seem too daunting. In this case, though, we need to look for a perfect cube factor. So in order to simplify, we want to pull out all perfect nth root factors. Okay, so in this case, we want perfect cube factors. So I happen to know that this is the same thing as the cube root of 27 times 2. Well, using that product rule for radical expressions, we can break this apart. We can take this single radical and break it into a product of radicals. So this would be the cube root of 27 times the cube root of 2. And it just so happens 27 is a perfect cube. So 27 is the same as 3 times 3 times 3. Therefore, forgot a little e, the cube root of 27 is 3. So the cube root of 27 is 3, and then we're just left with the cube root of 2. So that is the cube root of 54 in its most simplified form. Now let's say that you didn't realize that 27 was a perfect cube. That's okay. You can do that factor tree thing here too. So let's say we have a factor tree and you're like, okay, I know 54 is at least divisible by 2, and you find out that 54 is 2 times 27. Well, 2 is prime. 27 is not. So we need two factors of 27. And let's say you're like, okay, well, 3 and 9. So 3 and 9 work. 2 is still prime. 3 is prime. 9 is not. But 9 has two factors of 3 and 3. And you just have to always be mindful of what your index is. Since my index is a 3, that means I have to have groups of 3 identical factors. If my index was 4, I would need groupings of 4 identical factors. If the index was 5, I would need groupings of 5 identical factors, and so on. So in this case, I'm not looking for pairs of factors. I'm looking for groups of 3 identical factors. And I have that right here. So that tells me a 3 can come outside the radical. And then I'm left with this poor 2 right here. It didn't have those 2 other mates that it could pair up with or match up with to come outside the radical. So we're left with 3 cubed root of 2. So either way you slice it, if you just happen to magically see those perfect cubes that can come out of whatever your radicand is, great. If you don't see it, try the factor tree. All right, now part B, notice that we have a 5th root. So when you're dealing with a 5th root, your goal is identical factors, but groups of 5 of them, okay? So I know that there's no way I'm going to find groups of 5 factors of 8 or 12, so I want to push this all under one radical, okay? Now what you need to be aware of is when you're simplifying this, if n is odd and you have the nth root of negative a, that equals negative nth root of a. You just bring that negative outside, okay? It just kind of works out magically that way. You can have the negatives when you're dealing with roots that have an odd index, okay? So let's just make note that this final answer is going to just overall be negative. But for now, let's push all of this under one radical. So I'm going to go ahead and pull that negative out front just so I don't have to worry about it. And then I'm going to rewrite this as 8 times 12 times x to the third times x to the second. And remember, we're looking for groupings of 5 identical factors, okay? So let's start breaking down 8 and 12. Well, I know 8 is 2 times 4, but I know 4 is 2 times 2, so 8 is 2 times 4, but 4 is 2 times 2. So I know 8 can be written as 2 times 2 times 2. And then 12, I could write it as, well, 2 times 6, but 6 is not prime, so I could break down the 6, and I could write it as 2 times 3. So I'm going to write my 12 as just 2 times 2 times 3. And then I've got x to the third times x to the second power. So you remember the product rule for exponents. That's like a completely different situation from like chapters ago. That tells me to keep the x and add the exponents. So this ends up being x to the fifth. So by pushing all of this, merging all of this under one radical, we now have negative 5th root of 2 times 2 times 2 times 2 times 2 times 3 times x to the 5th. And remember, we're looking for groups of 5 identical factors. And guess what? We just so happen to have a group of 5 2s. That means the cube root of that chunk that's circled in red comes out as just a 2. So now we have negative 2, and then we're definitely going to have the 5th root of 3. But let's see what happens with our variables. Well, x to the 5th is x times itself 5 times. So this is a group of 5 x's. That means an x can come outside the radical. So this is going to simplify as negative 2x times the 5th root of 3. Okay, so we don't need to do anything too crazy. So I want you to understand the idea of simplifying, but I promise when you get to your pre-calculus class, you're not going to see anything too wild, but you do need to know how to simplify, okay? Let's look at part C and D, and then that'll wrap up this worksheet. So for part C, we have the 4th root of 64, and then we have the 4th root of 4. So we're going to divide the 4th root of 64 by the 4th root of 4. Well, the 4th root of 4 won't simplify. And then 64 will certainly simplify, but not completely. It's not a perfect 4th root, I don't think. So we need to see what we can do to simplify here. So let's see. I'm going to merge this under one single radical. So I'm going to say this is the 4th root of 64 divided by 4. And what we want to do is divide that quotient that's under the radical. Now, hopefully, you know what 64 divided by 4 is, but if you don't, jump over to your calculator and let me prove to you that 64 is divisible by 4, and you get a nice pretty 16 out of it, which is ideal, and we'll see why it's ideal in just a second. All right, so this simplifies to just the 4th root of 16. And then we're looking to see if we have a perfect 4th root or if we have 4 identical factors that can come out of 16. So let's think about 16. 16 is the same thing as 4 times 4. So we have 2 identical factors, but we need 4, okay? Well, 4 happens to be 2 times 2. This other 4, similarly, is 2 times 2. And look at that. We have 4 identical factors, so this tells me this was a perfect 4th. So this simplifies to just plain old 2. Okay, so if we had 64, we could have simplified it. It actually would have been a perfect 4th root, if I'm not mistaken, because you get, no, well, you could pull a perfect fourth root out of it, but it wouldn't simplify nicely all on its own. But by simplifying the fourth root of 64 and the fourth root of 4 under one radical, we were able to simplify it, and it turns out it was a perfect fourth root all along. You just couldn't see it when it was separated. Now let's look at this last example here. So let's see. I've got the cube root of negative 27 x to the 9th over 64 x to the 6th. We could do some stuff with this, but if we simplify the radical as it is, we're going to get just like a weird fraction that won't necessarily simplify. So what I want to do here is I kind of like simplifying this into two radicals, so a quotient of two radicals, okay? Because I noticed something about 27 and 64. So let's go ahead and break this down as the cube root of negative 27 x to the 9th divided by the cube root of 64 y to the 6th. And then what I happen to notice is that 27 is a perfect cube, and I think 64 is too. So let's just double check. Let's prove it to ourselves. So do you remember how to do a cube root on the calculator? Hopefully, if not, I'll show you. So we have a button right on the main calculator that does a square root, but we don't have one that does a cube root. But if we go to this math button, remember math is below the two colorful buttons. If we go to math, this option 4 will calculate a cube root for us. So we want to go to option 4, and then we want to type in negative 27. We should get negative 3. That's awesome. So that tells me that the numerator all on its own was a perfect cube as far as the 27 is concerned. Let's repeat that and see if 64 is a perfect cube. So 64, we get 4. So 4 and 20, or 4, 64 and negative 27 are perfect cubes. So we're going to use that to our advantage. And so by splitting this expression into two separate expressions, we're going to be able to simplify quite nicely. So for the numerator so far, we have a negative 3 that comes out. And for the denominator, we have a 4. Now let's talk variables. When you're dealing with a variable, it is a perfect cube if it is divisible by 3. Okay, so anytime you have a variable expression, if the exponent is divisible by 3. So anytime you have a variable expression, if the exponent is divisible by 3, it's a perfect cube. 9 is divisible by 3, so is 6. So x to the 9th and y to the 6th are both perfect cubes. The way you simplify it is you take the exponent and you divide it by 3. So we've got x to the 9th. We want to keep the x and then divide 9 by 3. So that gives us 3. We want to take y to the 6th. We're going to keep the y, and then we're going to take 6 and divide it by 3, which gives us a 2. So that tells me that by merging this under one radical, I was able to simplify this very nicely as negative 3x to the 3rd over 4y to the 2nd. Whereas if we had tried to keep it under one radical, we could take out pieces of it, but then other pieces would have been left behind, and it just would have been weird. So by breaking it apart, we were able to see that the numerator and denominator individually were perfect cubes. So there you have it. Instead of simplifying under the radical and then trying to simplify the square root or the cube root, we got something much better by breaking this into the two radicals, okay? So practice this. I will say that you're not going to see stuff too complicated when you get to pre-calculus, but you do need to understand the basics of simplifying radical expressions, especially those square roots. That's going to come up later for us in this class.